Good morning, good afternoon, good evening, depending on where you are on this fast forward planet, which is still wrapped in a pandemic. As I've been saying at the beginning of every one of these 360 shows or so, there was 1 billion vaccine doses wasted in the last 2 years, something like that. And there's still a couple billion people on the planet who've not had one vaccine dose. Lots of work to do. It's a human-heated planet, as my guests know better than anyone. Anyone who's experiencing what's happened in recent years has seen the impacts of the climate system, particularly amplified in places where human communities have built vulnerability or settled or been marginalized through poverty or prejudice into areas of climate risk. And we're going to talk about new frontiers and how to address that. We're in a world that's still wrapped in what some call an infodemic. Essentially, the communication environment is polluted, just like the actual biophysical environment can be polluted. One of the goals of my program here at Columbia, at the Climate School, is to find ways to mitigate the pollution and also adapt to what can't be constrained. And that's what these webcasts are all about. It's a planet that's in turmoil because of the invasion of Ukraine as well by Vladimir Putin, coming up just 2 months from the anniversary of that horrific act. And that's changing people's exposure to climate. Energy costs have skyrocketed. The world's in with a set of multiple challenges at the same time. Today, again, we're going to talk about climate change. And there's another frontier that's exploding, along with the ability to use science to probe and understand the climate system, both its inherent variability and the changes we're nudging it into. There's also artificial intelligence, which is machine learning using computers that can emulate and adapt and seemingly replicate lots of human capacities. There's a big question about whether that's intelligence. We'll find out soon enough. And this is a discussion of the interface of these arenas: climate science, data science, artificial intelligence, and resilience. How do we use the information that's being gleaned through those systems to build better lives for people in a changing climate? I've been at this for a long time. 1988 was my first big article on global warming. So that was parts per million year, 350. That was the year that the IPCC, the climate panel, was created. It was the year that I went to the Boulder Climate Supercomputing Centers. I'd been there already in the mid-'80s, writing about nuclear winter. And the supercomputers at that time are like a pale shadow of what we use today. This is just some video that gives you a sense of what the main insight gleaned with climate models so far has been. Yes, there is a human role in global warming, and almost assuredly, going forward in the century, we're locked in without extremely deep cuts in greenhouse gas emissions to a human-heated climate, and it's going to last a long time. That's been this profound advance through the IPCC history and the work of many of the people on screen here and their forebears. But there are big gaps in these models. There's some things they don't do well, and there's many reasons. There's uncertainty. We don't have a perfect picture of the world. There isn't clear understanding of clouds. Joni Mitchell's great song about clouds is still true. Everyone here is looking at clouds from all sides, and they do create challenges for us. Artificial AI, as I mentioned, is an astonishing tool. I'm just going to start things off in a humorous way by showing you a clip from yesterday's conversation I did. Here, I've got it set up here. I don't know if it'll do this or not. This is the Chat GPT, and down here I've typed in write a poem in the style of Andrei Codrescu. So this is Andrei Codrescu, who was a very prominent commentator on NPR for decades. He's an accomplished poet. And yesterday, live on screen on this webcast, I typed in write a poem. This is the chatbot from OpenAI. Write a poem in the style of Andrei Codrescu.
Oh,
so let's see what happens.
Okay.
Look at that.
Oh my. Must
Andre,
be a lot of stuff out
read
there.
it now. That's the way.
Yes. I'll make the type bigger.
Thank you.
Hold on a second. It's still going. Oh my God, this looks interesting.
Gee, it's right
Here
in
we go.
Canopy.
Yeah, that's pretty long for your stuff, but
The city sleeps,
so
a siren song of neon lights and traffic strong. I never rhymed my poems, but that's okay. The buildings rise, a towering might of concrete and steel, a glittering sight. This is about fifth grade, actually. The people bustle, a rushing stream of hopes and dreams, a myriad scheme. The air is thick with energy, a restless pulse, a symphony. This is truly dreadful.
so there you go. Computers are amazing. They're changing our lives in 1,000 ways, and it's hard to keep up sometimes. But we're going to talk about how this can be changing the lives and work and output of climate science. And we'll start with a little round of introductions. I pulled together some people here who are really the cutting edge of what's being tested and tried, and from different generations. An emerging grad student, a postdoc, young researchers, and people leading these big programs. So Pierres Background, LEAP director, is professor of Earth and Environmental Engineering at Columbia, as well as Earth and Environmental Sciences. He studies terrestrial water and carbon cycles and their changes with climate change. Galen McKinley, LEAP deputy director, this is the LEAP project you'll be learning a lot more about, is a Columbia University professor of Earth and Environmental Sciences and Environmental Engineering, focused on the interplay of ocean, carbon cycles, and climate science. Carol Lamb, to my whatever, right there, is an associate research scientist in Columbia's Earth and Environmental Engineering department. She has Department of Energy funding and is using machine learning and other data science to clarify the microphysics of cirrus clouds. Cirrus clouds are really important, high in the atmosphere. They can be reflective or not. Many clouds have different properties that can work in different ways in the climate system. And Oliver Watt-Meyer is joining us from the Allen Institute for Artificial Intelligence. He's a senior research scientist in the climate modeling group there. Oliver, where are you in the world? I can't remember.
I'm usually based in Seattle, currently in Olympia, Washington, so near Seattle.
Great. And Chad Small, a graduate student in atmospheric sciences at the University of Washington, who recently moved there, or you are moving there, sort of, kind of from the New York area, I believe. You're doing dual duty as an emerging journalist, science writer, and a grad student in atmospheric sciences at University of Washington. You had an article in the Bulletin of the Atomic Scientist, which I've written for as well, on frontiers and questions in climate modeling. I thought it'd be great to get you in here too. And University of Washington hosts some of my favorite climate scientists from way back. Mike Wallace there, I relied on from the very beginning. So it's great to have you all here. I wanted to ask you a sort of an initial question, each of you, just to kind of drive forward what it is about this question, meaning applying new technology to climate science to foster better adaptation. What is the driving force? How did you come to that question? Maybe we'll start with Pierre as the director of LEAP. So Pierre, what you could do many things with your skill sets, as we all can. Why this one? What's driving you forward?
So hi everyone. The kind of the background for that is that we need to understand that climate models are really, really expensive to run, right? So we need to run them on supercomputers typically, and we are still very limited in the scope of what we want to do, especially right now. The resolution is on the order of, say, 100 kilometers to 100 miles, right? That's roughly the type of resolution we have. And at that scale, really the main trouble is that we cannot resolve things that are really important. You mentioned cloud before, or you could talk about ocean eddies or a lot of different processes. A lot of them are happening at scales that are way, way smaller. So for instance, Kara is working on things almost at the micrometer scale, right? And a lot of that we cannot really resolve. So kind of the hope that a few of us had like a couple of years back is that potentially machine learning could be used to actually reframe the way we do climate modeling and trying to use that as a way to be much more accurate in terms of the projections we are doing. Because again, we are trying to represent things that are very complex and very small. So it's very difficult to do a good job at representing them. So that's why a few years back we thought, like, why don't we try to really apply that at scale, like, and hoping that we will see the same or witness the same type of revolution we've been witnessing in some other fields, such as in medicine, for instance, or looking at the web, So that's kind of the background for that, at least in my perspective.
I think you're muted, Andy.
I'm muted because we're dog sitting and someone's missing his mom. I think it was just a week or so ago that NASA celebrated the 50th anniversary of the Blue Marble photo. And there was some recent work by, I'm pretty sure it's a European modeling group, although they're all international, that was showing, on the left, you see how models resolution has improved over time. And here, essentially the model is close to replicating this 1972 image, which is so pivotal. And there you have the simulation of the Earth. We'll get more into this question of qualitative and quantitative simulation. In other words, something that looks like the Earth, works like the Earth, but is it really representing accurately what we need to study more clearly going forward? Kara, when if I asked you that question, what gets you zoomed in on this? Was it clouds? Was it something about clouds? Was it something, again, with your physics and math work, you could do pretty much anything. So what about this question fixates you?
So actually, I guess before I came to Columbia, I was a researcher at NOAA working on aircraft observations of aerosols. And it was actually a problem that I was having trouble solving, which was like we put these instruments on planes and measure all these signals from aerosols. And so from a typical flight, we'd get like millions of different signals, but then trying to filter through those and figuring out, these specific types of aerosols that we were interested in identifying, like how could you do this? And so like this was how I actually got interested in using machine learning methods, because it was so useful for like these problems of classification. So I think like from that, it was, I saw like just like digging more into this, just seeing the potential for like how AI could actually be very transformative for atmospheric science and for climate research, and like give us this new set of tools and this new way of looking at problems that we didn't have before. So from that, I was just really interested in learning more, and also like seeing how these methods are being applied like in computational biology or in physics or in chemistry, and like how they've really revolutionized those fields. Like I feel like in climate research, we're just right now at the forefront of like getting at that revolution that we've seen in some of these other fields. So it's just like an exciting time to be in this area of research.
That's so interesting about the cross fertilization, or seeing something applied in one arena and then bringing it into this arena. Galen, is that part of your learning curve, or sort of what propelled you forward when you think about this challenge?
Yeah, I'll take it from kind of maybe a little bit more of a personal perspective here. This science is fascinating that I do. I work on the ocean carbon cycle, and we want to understand how the ocean is mitigating climate change by absorbing lots of our emissions. But we're not mitigating the way we need to. And I have 2 children, and I want to leave them a world that is healthier and is not, plagued by all the changes that we can predict. And I do think that the more we can move forward with our predictions of the climate, make better estimates of where the climate is going, the better we can help the world both prepare for adaptation, work towards mitigation. And as we move through the next decades, where we both have to mitigate in order to preserve the climate for our children and our grandchildren or our great grandchildren, as well as deal with a lot of adaptation to changing climate, the better information scientists can provide to the world, both about the carbon cycle, that is the key for addressing on that mitigation side, how it's evolving, why is the atmosphere not changing more quickly, questions like that. The more we can do that, the more we can predict physical impacts. That is the service that that society needs from the scientists, right? And we haven't reduced our uncertainties as much as we need to. And AI offers an opportunity to bring in all this data to our climate models. And so we really need to take advantage of that for the benefit of society, to inform society. Ultimately, society has to decide what it's going to do. That's a collective decision. But what I think we can do as scientists is provide better information.
That's great. And a big part of the LEAP project, I mentioned the name before, we'll just talk about this in a minute, and then we'll get to the Allen Institute and Chad's writing and Kara's work. So LEAP, let's just, before we go forward, I should ask you how this came about. I'm involved with this a little bit, as everyone who read the primer might know. I'm on the knowledge transfer committee of this project. It was a proposal for a science and technology center for the National Science Foundation, which has funded these projects periodically. And I'd love to hear from Pierre and Galen a little bit more about to me, what Galen just said really is at the core of this. It seems to be back in the 80s when I was first writing about this, in this era, it was the climate models were basically being used to verify that global warming is happening and real, and some projections. But as you've all said, the resolution and sort of approximations have made it less than useful sometimes for specific purposes that society wants. And LEAP seems to be really built around that. It's not just the science, but integrating it with decision making. So Pierre, maybe a little bit briefly from you on when did this start? When did you start pulling this together? I came in kind of late, I think.
Yeah, so that was a few years back, actually, pre-pandemic. And I think a lot of that started back in 2018, 2019, when we were basically a few folks at Columbia doing ML for various problems. So for instance, Galen was using that for carbon dioxide over the ocean. I had another colleague, Ryan Abernathy, also trying to use some of that for ocean physics, plus some colleagues that just happened to be arriving at NYU Lausanne in particular. So there was this convergence of people starting to use those tools on basically the whole climate system, for the biogeochemical cycle, for the the physical system as well. And really, it was very clear, at least to me, that, we were very kind of isolated in a sense that we had separate projects, but to really advance and make progress, we needed to be collectively trying those things and be collaborating more with the machine learning folks, So it was really trying to be more of a synergy and a community driven, and hoping to exactly get to this revolution that Kara mentioned earlier, that potentially we could do the same that we are seeing in the pharmaceutical world or in the chemical world. And again, basically bringing forces together, if that makes sense. And for me, but that's different for everyone, but at least to me, kind of the final objective was really, can we revolutionize the way we do climate modeling? Can we have this leap? And that was why we used that term, a leap in the quality of the climate model projections, as we call that, so the long-term prediction. And basically to connect to users and to people that will actually need to have relatively good accuracy climate projections. People want to know whether they will have more or fewer droughts. They need to know what will be the change in the frequency of flooding, things like that, or number of days of heat waves. So things that are pretty tangible, but at the same time, it's a bit disconnected with what current generation of climate models can actually provide. So it was also to try and reconcile those two things, if that makes sense.
Yeah, actually, Galen, we'll get back to that in a minute. I want to finish the round of introductions. I'm sorry, I haven't had quite enough coffee yet. Even it's already afternoon. Chad, what's your journey been? Again, you are pursuing two tracks, it seems, writing and inquiry in science. What pulls you toward this arena?
Yeah, I think particularly in this question around modeling, it's really trying to nuance the conversation a little bit and not like nuance it in a way that makes it inaccurate, but nuances it for people who think it's really binary. So for example, like there's climate skeptics who feel like the models are like wrong, and then there's a lot of people who are pro models who feel like the models are like always correct. But there's really like a nuanced perspective of like the models can get us to a certain point without, like as everyone says, being quite perfect, right? And I think that's a really good thing to let regular people know. Because at a certain point, if you want funding for this kind of work that makes the like machine learning models better, that makes climate models more robust, people need to know why it matters, and then push policymakers then therefore after that to invest in this kind of work. So for me, it's really just been like a curiosity question and trying to like clarify for other people, because like my own research interests as a grad student aren't necessarily in this arena, but I think like for anything that you're doing with regard to climate science or atmospheric science, this kind of stuff will be helpful in the future. So it's very much clarifying it for others, but also for my own like interest as like a curious person and just like as someone who enjoys writing and communicating to others. So that's kind of where my journey has been so far.
Did you like when you were in high school or even before? Was it the writing part that was in the foreground for you, or science? Or
If you ask like high school me, it'd be more science as like as a thing I was interested in. I think as I got older, I started to get more interested in the writing part of it. I think I always like enjoyed writing, but if you're like 17 or something, everyone tells you that science is a more like stable career trajectory and stuff like that. So you kind of have to like work your way through it to find a space to like do both, I guess. So for me, it was very much just like working and then coming back to school and then saying, well, actually, I do enjoy writing, but also I enjoy the science, and there has to be space to do both. And I think that that's really important because whereas interdisciplinary work in the sciences always usually speaks to the idea of doing like, whether you're doing atmospheric science or oceanography and combining those two together. But I think there's a space to also bring communication to that too and writing to that also that I think benefits them both. I think that if you want more scientists in the future, it's kind of an idea of communicating with people who are younger, who might want to go into it, who don't know why it's important or perhaps like what they can do with it. So that's kind of where I come to, if that makes sense.
that's great. Yeah, and as Galen and Pierre and Kara know, again, LEAP is this big component on both education and on equity, and connecting the science with communities that have been excluded historically from these fields just by the deep history of uh, how things played out for race and other communities on the edges of possibilities. So it's great to know that, well, the more people can demonstrate these crossover dynamics, the better. I'm really glad you're in the mix here. So, Ollie, John Allen created a lot of things.
Paul Allen.
Paul Allen, oh my God! See, there you go. He created a lot of things. He left the world way too young, and the Allen Institute. Oh, am I freezing? By the way, I think I mentioned. I haven't told the public yet that I'm on. I'm not on a hardwired internet connection. I'm in rural Maine, Wabanaki territory here, and outside the town of Ellsworth, and we have too many trees on our property, so the galaxy of Elon Musk's satellites sometimes get blocked. Anyway, so if you couldn't hear me earlier, he created this Center for AI as part of that constellation of things he left behind. And why is climate a big part of it? And why is climate a big part of your work?
Yeah, absolutely. Yeah, I mean, I think for speaking for not that I can speak for Paul Allen, but certainly what I've heard in terms of how the project came about. He was a software engineer. That was his training, and that's where he came from. And I think he was fascinated and maybe shocked by how archaic climate models are. You mentioned them in your description as cathedrals, and that's a really nice analogy for these things that are constructed by multiple generations. But cathedrals are kind of hard to start over, and so
Right.
We're kind of in this situation where we have these pieces of code that are integral to our climate models that were written 30, 40 years ago are really hard to actually read, are hard to build off of, and so he was kind of interested in, okay, can we, is there a way we can kind of reshuffle this whole thing and try something new? And I think that was his motivation for kind of funding a new project. that can kind of reimagine these things. And so there was actually two aspects to the project as it started. There was the part that I'm working on, which is using machine learning, trying to address the issues that Pierre was talking about earlier. But there was also another side of the project that was actually taking an existing model and trying to rewrite it basically in a new, much more readable language that would also run much more efficiently on our modern supercomputers that are using new architectures, using GPUs, graphics processing units, which are much more capable, can potentially do a lot more computation, but require really different programming paradigms. And basically, none of the existing climate models work on these new architectures. So I think that was his motivation, was really, let's drag these things into the 21st century from a computer science perspective. Speaking personally, I've always been interested a lot, really, in seasonal forecasting. That's been a lot of I think what's driven my motivations, and actually where I think AI might make an impact first in this sphere. And so that kind of went my PhD work, working as like kind of esoteric theoretical things that we're motivated by. Okay, if we understand these processes in the atmosphere better, we can make better forecasts on like 1 to 3 month timescales, which is a really challenging timescale for making forecasts, but one that's extremely useful for planners, people managing hydropower in Washington, for example. And so that's kind of where my scientific interests started, and I've kind of been moving in a more and more applied direction. So starting kind of understanding the theoretical basis for these kinds of predictions, then now working on actively doing model development and trying to make these models more accurate. And then on the AI side, I mean, this is definitely something that I've come to more recently and just kind of started working on in the last 3 years. But it's certainly something that I've been kind of tracking for a long time. And I was reflecting on this before the call, and I was remembering I actually went to this talk by Geoffrey Hinton. So Geoffrey Hinton is one of the pioneers of AI, and has been working on machine learning and deep learning for decades. And he had a really foundational paper that he published with I think a graduate student and a postdoc in 2012. This is the so-called AlexNet paper, which is basically the first paper that showed that you can use neural networks and deep learning. And they basically had this, as Pierre describes, a leap basically in the quality of image classification. So, is this photo a cat or a dog, and obviously we've gone way past that now. But at that time, it was this incredible leap. And so I was lucky to be at University of Toronto doing my physics PhD. That's where Geoffrey Hinton was. So he gave this colloquium. Usually the physics colloquium, the room's kind of half full, and maybe sometimes there's someone falling asleep in the back, maybe. But this was just like totally different. The aisles were packed. There's 500 people in the audience. It was a couple of years after that paper came out, so it already made a big splash, and it was just really exciting to see, like, wow, just how quickly progress was happening in that area. And so that was quite a while ago, but I've always been kind of interested in AI. And so when this opportunity came up to join this project at the Allen Institute, it was kind of a no-brainer for me.
So there's that word, leap. I think a foundational goal at the project at Columbia too is really making a breakthrough. And maybe it's time to zoom in a little bit on where, this would be for Pierre and Galen, maybe Galen first, when you look at this matrix, and it's pretty wide, we have Kara looking at cloud microphysics to seasonal variations, La Nina, El Nino, all that inherent variability that matters on these timescales you're talking about with LEAP. What are the cogs in the wheel that, Galen, that you see most tweakable?
Yeah, there's many things in the climate models that we want to address. I will say the way we sort of break that down is into 3 main areas. One is, can we replace some of those underlying equations in the climate models with representations of processes such as clouds or ocean eddies that are more informed by data, essentially using machine learning to harness either high resolution simulations or large data sets to better represent how on the scale of a climate model grid cell, which is rather coarse, hundreds of kilometers by hundreds of, or tens of kilometers by tens of kilometers, let's say, how can we better put a cloud that is only has a scale of a few kilometers at most into that, sort of like the pixelated version of that you were showing in some of your videos. So can we use machine learning to do that? And the other end of the spectrum, where we have very little data, we are working to improve the availability of data products that sort of extrapolate from sparse data to the global coverage that our models give us, to try to provide a better basis for comparing our models and identifying the places where they're not doing well, and then comparing across models, for example. And in the middle, there's sort of a middle range of efforts that are trying to do things such as say, well, we think the structure of our model is okay, but we don't know what the parameter settings are that are going to best represent how these things operate across scales of space and time. And so we're going to use data to sort of tune our models to look more like the real world, with the hopes that then we have better understanding of the future. We can also use machine learning to expand the state space in which we can make those kinds of estimates. In terms of geophysical areas, we're working in the atmosphere, we're working in the ocean, we're working in the land biosphere, we're working on the cryosphere. So across all the areas, we're trying to do some projects that make progress, but we're also hoping to build tools and a community of learners who can then do more on other problems going forward, right? So it's not just there's not just a few things to work on, really. We think that the tools and the skills that we are developing can be applied across so many different areas.
That's so interesting, because what you just said about integrating the education model, the work of it's like going back to the cathedral building that I think about here. You got to sort of be training the next generation working on the cathedral, even while you're doing the work with your tools today. And that's pretty well integrated. I don't know how unusual this is within academia. I don't know, Chad, whether you've been familiar enough with what's going on at the University of Washington yet, but it feels to me like on all of our big problems of sustainability, we need a lot more of that. I hadn't thought about that until just now. Sort of creating an initiative where you're also looking ahead and making sure there's people in the pipeline to do the machine learning science and the other science going forward. Is that still an outlier position? Ollie, you're also at University of Washington, or you had been, so, or just elsewhere. Have you seen that? Does this feel important to you guys, Chad and Ollie?
Yeah, I mean, I think it's definitely a challenge. I think, for like speaking, I guess, our group, and also looking at, the people on this panel. I mean, we're all kind of more domain scientists, right? Like coming from some kind of climate science or physics background, and picking up on the AI things. But I think it's also important to have AI experts and that are tightly involved in these efforts. And so that is, that's something that I'm excited about being at the Allen Institute for AI. We do have support that we can lean on in terms of real world leading experts in sort of fundamental AI practices. But I think that's definitely going to be a challenge of training people who are kind of capable in both these areas. It's definitely not easy.
And, Chad.
It's the same point. I think there's a big push in across atmospheric sciences in general to kind of bring in people who have expertise in AI to work with the scientists and make them much more robust in this space. So I think there's a push broadly across the board, at least from what I can see so far.
And Kara, in your educational track so far, how much has interdisciplinarity been hard to fit in, given the strictures and demands on a young emerging scholar?
I would say one opportunity that I've gotten involved in the past couple of years is working with Frontier Development Lab, which is this program that brings together Earth and space science PhD students and postdocs, and puts them with PhD students and postdocs in machine learning, and works for a short 8-week period on these like specific challenges. So like that for me has been like a really nice framework to see how these types of collaborations can actually work. And like, at first when the challenges start out, people are sort of having some trouble figuring out how the domain researchers can communicate exactly what the problem is to the computer scientists, and then the computer scientists can know which tools are actually the most useful to bring to those problems. So personally, like seeing those types of opportunities, and then also with something like Leap, where it's being able to do this now full time, to think about how we can work with like researchers across fields, like this can like really foster these like interdisciplinary efforts that you see the progress happen really quickly because of this ability to work together. So
What was the name of that tier? One? Did you say one tier?
The
development lab?
Oh, Frontier Development Lab.
Oh, Frontier Development Lab. Okay.
Yeah.
Sorry, I misheard. That sounds like a pretty valuable entity. Is that, does everyone here, is that familiar to others here too? It just seems like we need more of that. Whatever. Is that an independent?
It's run independently, but they collaborate with NASA and ESA in Europe, and then like each summer, and I think also they've recently started collaborating with the Department of Energy on different challenges. So it's been, I think, since 2016, and they've put together like different challenges.
That sounds great. The NSF also has this convergence track of. There was a sort of a grant offering. I was involved with another one at Columbia that didn't end up going forward, but there seems to be an emphasis on convergence and fostering crosstalk and the like. But how do we move from convergence as a word to outcomes is a big question. There were some postdocs at Columbia 2 years ago. They wrote a paper in Nature Sustainability that where they laid out sort of what academia would need to do to really not just to move from disincentivizing interdisciplinary scholarship to fueling it. And the things included like time, especially for early career, scientists. And I think it was Megan Maurer, I think she might still be at Columbia, on this webcast with Alex Halliday and others. She said, essentially everything is kind of still cutting against these things. What she said is it takes time to develop the fluency with other disciplines. It takes time to build a trusting relationship with communities if you're doing community-based research, which is less what we're talking about here. But that's the thing that you don't get. So you end up writing more quotidian papers, you write papers that are just in your discipline, just to get in the literature, to get published, get forward. And so you have this lost, it just doesn't fuel the change that you would need. Galen and Pierre, from your standpoint, have you seen that? You're more senior now, but you're still pretty young, both of you. Do you feel like there's a change afoot here? Or is it still early days in trying to sort of move from the old model that doesn't seem to really work well with what Leap's trying to do?
Pierre, you want to take that one?
Yeah, go ahead. Yeah, I can take it. It's up to you. So I would say, I've been thinking a lot about like this convergence between different domains. I think it's tricky because it's also like my personal feeling is also what is the reward system, in academia, that's also what actually defines a lot of the work we do, right? And when we are thinking about things such as Leap or things that are at the convergence, it means that you will be evaluated by two groups of people, right? Which is not that great, right? If you want to go through the academic system, it's better to actually know your network, right? And you really need, in that case, to go well beyond a simple network, and that can be an issue, The hope, though, is that in the long run, indeed, if there were to be a revolution, it would be great to be at the forefront of that, and it would be great to be part of that revolution. But we need to, at the same time, be cognitive of the fact, especially for younger scientists, that we need to have some sort of sheltering of them because they are going to do like interdisciplinary type of research that takes longer, just math, right? You have two disciplines, so you need to learn or no, almost twice, maybe not exactly twice, but almost twice the amount of work, the bibliography, the referencing, etc. So it does take time, right? And so I think that's also kind of the value of long-term funding, whether at the Allen Institute or in LEAP, and going beyond a short-term type of funding. So for people who are not familiar, typical funding is for 3 years, which makes it really, really difficult to create convergence between disciplines, right? You need to have a long-term program to really create this new generation of scientists and really from the bottom up, right? So long-term funding is extremely beneficial for this type of interdisciplinary work, right? And that's hopefully how we can actually build long-term, potentially that would be a new discipline, or at least at the forefront of things we can do.
And does anyone else have thoughts on that idea of, I guess, let's say, what would a vision of success be in academia? Do we have to truly break the system to really foster the kind of work that you're all pushing forward on?
I mean, I think that this is one of the things that the STC, the Science Technology Center from NSF, really pushes, that not all, even large grants do, is this idea that it's not just about doing the science, it's also about educating the next generation and educating them in a way that is interdisciplinary and in a way that addresses the particular problem you're working on. And the SDC program from NSF has existed for like at least 40 years and has shown its ability to really transform disciplines, add new intersections between disciplines. So that is what we're trying to do here. I think we're very grateful to the NSF and the taxpayers of the United States who support the NSF for allowing this kind of work to go forward. But it doesn't, but I would agree that it doesn't happen often enough. We are siloed, and largely because of the reward structures that Pierre mentioned, there isn't enough time to learn new things. And we need to think hard about developing innovative educational programs that spur that process and encourage all of our colleagues to support their students in taking those steps.
Great. Well, I want to bring up another sort of a track here, which is if you, we're going to get to this more in some future conversations. This is just, I should have said earlier, this is the first in what will be a series through the coming year on this intersection of AI, data science, and climate science and impact. So the question is, on the impact side, if we could start with a scenario where, and it's another way to play the game of how this could be fast-tracked to address problems in the world. So right now, Somalia, yet again, because we've had, I think it's a triple La Nina, or is it quadruple? I can't remember. Ali, I know you work on that stuff. A bunch of people at Columbia do.
Triple dip.
Yeah. So here we have a situation where you've got energy and food prices have spiked because of the Ukraine situation and inflation. You have fragile states across peri-Saharan Africa. You have a crisis still again in Somalia. And if we wanted to get a better idea of what would climate change do in a way that could actionably change how the FuseNet is kind of a famine early warning system. So I would think, to me, it would be really cool to think there's some improvement that could come through these processes in the coming years that could help the sort of planning community around aid, and not just aid, but proactive work. Maybe we'll start again with Pierre, because you're leading LEAP. If someone from, I think John Furlow, who's at Columbia, another part of it, came to you and said, what can we do better? Is there something you guys can do for us? What would that feel like?
So I think there's a couple of things here. The first one, and maybe that's also linked to what Galen was mentioning before, is that, so for instance, within the center itself, we are trying to do research, education, but there's also a big component, which is, as you mentioned before, Andy, which is on knowledge transfer, right?
Right.
And that actually goes back to the point that Chad had earlier, which is, it's not just about trying to do the best science ever, or in that case, giving you the best prediction ever. Is how do you actually put that information in the hands of the people that need it the most, right? Mm-hmm. And a lot of that is actually non-existent right now. I mean, we have sporadic efforts, actually some of that happening at Columbia, at IRI, but it's still very limited in scope, right? What we can do. So I think there's really a huge information bottleneck. We are not completely in the dark. Of course, things can be challenging to model, but we are not completely in the dark. And a lot of the things we do and a lot of the planning we do is actually very uninformed, and so there's really a big piece here, which is really connecting the science to where it's actually needed, and I think we are lucky enough, again, in the center to have some component on that in terms of knowledge transfer and trying to develop a platform so people can get access to such data. But that's, I think, an important component. The second one is our models, again, up to the task. We're asking them to predict things. So in that case, that could be, you would want to know like seasonal forecasts, or you would want to know some interannual forecast to know whether you will see a drought next year or whatnot, and that could be for agriculture, it could be for the insurance or reinsurance, because they could be actually insuring those crops, especially over large regions. But there again, a lot of the models are really struggling, in fact, oftentimes what people do is they just use the typical average seasonality, so the typical summertime, and they don't want to really take a stand there. And that's a huge bottleneck again, because it means that we are trying to predict what's coming up next, trying to inform people, trying to, for instance, distribute some support, like the UN, for instance, or I was talking to some other folks. I mean, they have different timelines, at the sub-monthly timescale, say for hurricane, so they need to know where the hurricanes are going to hit, and then longer timescales, say for drought support, But if you're not super informed, or the quality of the information that you have, which is at the end of the day coming from those models, if it's deficient, then you cannot really plan, right? I mean, you cannot reallocate all of the UN forces to all over the globe, right? You have to be targeted in some sense, and that's a huge bottleneck still, I believe.
Yeah, there was just a report. I did a piece on this. I think I wrote about it. One of the UN agencies came out with a report with some partners on trying to make the whole field of sort of hunger and disaster response, to bring it forward to being proactive. So you're staging, your planning for where you need food shipments is not always, oh crap, now we got to go over there. And that feels really important. Ali, is that something the Allen Institute is engaged into? Like, I guess maybe let me back up and say, just as Galen was saying about sort of training people to come into the field to keep the whole system moving forward, all the way through here, I guess part of the thing that's needed is more of that, just talking to people in these arenas more. So it's not just AI and climate modelers talking, or cloud modelers, but AI, climate modelers, disaster response folks, people in communities or working with communities at risk anywhere. That seems to be another layer that's just implicit. Ali, I know it's part of what's going on at Columbia too, but is that happening more widely?
Yeah, I mean, I definitely agree. It's a long chain. I'd say we're a little more on the on the modeling side, and a little less on the directly communicating these predictions to end users. But I guess our main kind of point of contact is we are working quite closely with scientists at NOAA, in particular at the Geophysical Fluid Dynamics Laboratory. So they're the people who basically develop the engine that's used for the model for weather prediction in the U.S. In addition to used within some climate models. And so that, I think that's kind of our way of staying connected and making sure that the things that we're learning, are being shared with the people that are developing these models and actually doing. And we're not, I would say our role is trying to be kind of the spearhead of finding these new techniques and figuring out what's going to lead to these advances. We're a pretty small group. We're like seven or eight people. And so, I don't think that we're quite in the position to be taking on responsibility of, okay, we're going to be making these projections, and sharing them directly with users. I think, there's people who know a lot more about that. And so, it'd be kind of shy away from taking on that responsibility.
There's a couple of questions we can start to get to here. Michael Katowski was helpfully putting that Frontier Development Lab website on screen here. But Mohammed Chavashi has questions related to your work, and they're kind of technical, but hey, here we are. Let me see. Mohammed Chavashi says, Ali, please share something about how you feed your clusters. Maybe you could, I'm going to go, he has a couple of in a row here. Here's the same thing, clusters with data. Are there some real-time sensors? So let's talk about data, and which, the whole garbage in, garbage out part. And Kara, I know you're working on this too. But Ali, can you tell folks a little bit about some of the technical side of this, like how you find data, how you figure out how to work with it?
Yeah, that's a big part of the day-to-day work. Absolutely. Yeah. So I think in our approach, and which is also being used by other folks, often what we take as our training data, what we're trying to learn from, is these ultra fine resolution global models, where you basically are taking this brute force approach and try to simulate what's happening in the atmosphere across the entire globe at something like a 1 to 4 kilometer resolution. So each pixel is that size, and that does actually let you represent certain processes explicitly that are not being resolved in kind of your typical climate model. So there is really a fundamental change there. You basically, when you run it at that resolution, you can just turn off part of the model, which is nice, because that part of the model that you're turning off contains a lot of assumptions. And so now we don't have to make those assumptions. So that's great. And so that's what we use for our training data. But the problem with that is that it's extremely expensive to run those simulations. And so those are usually run by our partners at NOAA, on one of their very large computers. The costs can be like in the hundreds of thousands of dollars for a single one of these simulations, and so we can't do that for, say, run that model for the next century, to know what's going to happen on these longer time scales. And so that's really where the machine learning comes in, is to try to learn from that really high resolution data, what's the relationship between these really fine scales and the broader scales. And once we have a machine learning model that represents that relationship, we can plug it into one of these coarser resolution models, which are much more cost effective, and we can do many forecasts, many predictions for a long time.
And I'd like to throw that to the Columbia folks here too. When I was, I guess, probably the first 20 years of my climate reporting, from 1988 through the early aughts, the whole improving climate modeling challenge seemed to just be about brute force. It just seemed to be about bigger computers, more computer time. But this seems much more refined and nuanced. And at the same time, computers are getting bigger and more powerful. For the same kind of question, how does the LEAP project, how much of it is focused on that end of the pipeline? How do you manage and assess, use these tools to improve the inputs? Maybe Galen?
Sure. Yeah. I mean, I think so I think, yes, brute force has helped. Adding resolution has helped. The other revolution that's happened really just in the last 20 years is the availability of data, the number of Earth observing satellites, the availability of in situ sensors. It's not just, high resolution models like what Ollie talked about is definitely something we're trying to take advantage of as well. But those don't exist, for example, all like land carbon fluxes or ocean carbon fluxes at the global scale. We don't have that. So in those cases, we're more trying to learn from actual data, and we have a lot more real data. It's sparse. It's not homogeneously distributed. There are a lot of issues that each individual project has to deal with. But still, the more we can scale up from the data we do have to understand the global scale, the better off we can do. So our approach at Leap is an all hands on deck approach. If you can run a high resolution simulation and that's the approach, we'll do that. If we're using data, we'll do that. You know, whether it's data from decades over the surface ocean, as in my case, or whether it's a field campaign over a glacier for a few weeks a couple of years ago. All of those data, trying to build teams across people who are using different kinds of data to learn how to apply AI, and it's different in each case. It's not the same AI in one case or the other. And then also, as was mentioned before, bringing in experts in machine learning who can help us to make better choices about the directions that we pursue and to collaborate with us. And then the last thing we're trying to do is also work on the AI itself to be better constrained by the physical processes of the real world, right? So machine learning in and of itself in its basic state is just like a fit to data, and it doesn't know that, for example, mass cannot become negative, or you can't lose energy from the climate system. So if we can build machine learning tools that respect those physics in various ways, that can also, we think, help make those tools do a better job of predicting the future when we, you never have data for the future, so you have to use a simulation to get there, but we want to obey the physics as we do so. So that's another thing we're trying to do.
Wow, so everything is a moving target. I'd left out the accumulation of data opportunities. Just amazing. I've written about the Argo floats, the oceans, which had been, ship track data, only where ships were. Now the oceans are full of buoys producing vast arrays. Astonishing. Kara, I thought before we go to some more questions, I did want to get into the specifics of that close focus work you do on one of the tiniest components here. So what's the challenge there with Cirrus Clouds, and why is the energy department interested, and how do you prioritize in your work?
Sure. So for Cirrus Clouds in particular, we're interested in these because of their climate effects. So these are like high altitude clouds that first have pretty important radiative impacts, so how much light is being reflected by them. But we don't fully understand how the shapes of ice crystals are determined right now. Like, just from a physical perspective, we don't have a good understanding of ice growth at these temperatures. And then also they regulate how much water is entering the stratosphere from the troposphere. And so stratospheric water vapor is an important greenhouse gas. So there's a couple of different important climate implications of these clouds. And so for this Department of Energy project, we're interested in just fundamentally understanding whether we can do a better job of understanding ice growth at low temperatures, like using a bunch of different data sets. So one of these are, like, as you see here, these cloud particle imager probes. So for the cloud microphysics problems, we really aren't able to get a good constraint on these processes just using remote observations like satellites, because we really need the details of what's happening really locally. So we need information from things like balloons or aircraft observations. And so over the past 20 years, there's now been a compilation of quite a lot of these aircraft observations. So what we want to do is actually use a large database of about 12 million of these crystals and ideas that were developed through like deep learning methods to actually try to get information out about what specific details of the crystals we need to actually represent in models. So a lot of the work that's been done so far has just been classifying ice crystals. And so I actually want to be able to go beyond just this classification and see if we can actually learn something about the physical process of ice growth directly from the observations.
But to be quiet of the night.
Sorry, that was the wrong slide. I was going to show something else. Didn't want to go back to the poetry. I have your work here highlighted. Hold on a second. And what's interesting here too is there's physical work that's integrated directly into the machine learning work. Let me just make sure I have the right camera, the right screen. Sorry, there's no producer here. It's just me. So there was an article written about your work recently in the State of the Planet blog. And this again seems to introduce a whole nother array of folks who need to talk to each other. The engineering is not just software engineering, it's hardware. So has that been easy, hard? How much of the work is translational, I guess I would say?
Yeah, I mean, I would say having done a bit of both, I'm, actually developing instruments to make some of these measurements. Like, this is very challenging, and why we probably don't have as many measurements as we would like is because there's still, like a lot more work that could be done on like the observational perspective, just getting more data and the right type of data. But I think that's something that can also be improved using like these, like the data that we do have, we can make better use of, because it is hard to get this data. So like, that's where I think like the machine learning methods can actually be really useful, or some of the other data science methods that we can actually make the most use of the data sets that we do have.
Okay, well, and where does this, what is the one of the other things I wanted to ask too is this, this came up earlier in the context of the NSF STCs, the Science and Technology Centers, having a long commitment. But when you're doing work on an energy department grant or the like, is there some hyper expectation of a result that might not? Are these longer term challenges? How do you manage that, the expectations and funders and the like? And that's actually a question for everyone here. Are they sitting waiting with bated breath for like a new, much improved picture of the dynamics of these particles in clouds by like 3 years from now?
Yeah, I mean, we're hoping to be able to like ultimately improve how how these ice crystals are parametrized, or how they're represented in models. So for me, that would be a success, and that we're like, using, here you're showing this picture of, this is from these cloud chamber experiments. So we have observations from cloud chambers, which are these fairly large simulation chambers to represent cloud processes. We also have single crystal experiments. This is work done by a collaborator, Jerry Harrington at Penn State. And then we also have the cloud particle imager probe images that have been compiled from these past aircraft campaigns. So if we can better understand how to use all of these, how all of these different observational sources can inform our models together, whereas like previously they've been used somewhat piecemeal, like that to me would be like a success, that we can, use the different advantages and limitations of these different methods, and to improve our models.
Okay. I think there's a couple more questions here, and thank you all for, here we are right up against the holidays, and it's great that you've been able to spend some time on this Sustain Wet episode through Columbia Climate School. We're going to probably wrap up soon, but I wanted to see, I thought I saw another question. Oh, well, Mohammed says, 1,000 thanks for mentioning some of the technical background. And, oh yeah, here, Sarah Younger, I guess this is the an important question. Are we making progress on the most difficult things to solve? Shouldn't this be where we apply the largest effort? Well, you're all, the climate problem is like the biggest problem in history, right? It's every problem. It's energy needs, balancing energy needs with climate impact, so many lenses. I guess you all have chosen a very particular part of the framework around that problem to focus on. My answer to her would just simply be that I think we need a lot of dispersed investment here, that there's no, the question of what's the most difficult things to solve is just as, I could answer that in many different ways. Making models better is big and important, but helping people in Somalia next year is big and important, because those kids, if they get to school and get well fed, can be innovators in the future. I don't know if you have your own answers for that kind of question. Just if anyone, just raise your hand or just pop it, just say, speak away if you want. Yeah, Pierre.
Yeah, I'd be happy to take that. I've been thinking a lot about that, and especially comparing that to theoretical physics, right? And the type of investment we've done at scale there. I don't think we are anywhere close to what we should do, in terms of climate effort, and that includes, as you said, like climate modeling, climate adaptation, and mitigation as well. Now, one issue, and that's very much related to what you just said, is that it's the fact that climate change is really big, right? It's a lot of different things, right? It's not just one thing. It's about predicting droughts. It's about removing carbon from the atmosphere. So a lot of many different disciplines, at the same time. So inherently, that makes it more spread out, like in terms of the effort that we would want to have. It also makes it more challenging, right? Because it's not just one thing, right? We are not trying to just observe boson, which is a very, very clear objective, right? So, but still, I think at the end of the day, I think Sarah is really completely right. We are nowhere close to a tiny fraction of what is needed, really, because that's the biggest problem of our time and potentially of history and humanity, and we need a lot more investment so that we can actually do things at scale and we can really fight that and potentially get back to normal.
Anyone else get that same feeling?
Well, I don't know if I get the spot. I was going to put this, to Chad, just because I feel like when you're starting grad school, it's like the moment of like, what do I want to work on? So I don't know. I'm curious, how did you arrive to, choosing the department you're going into or things you're working on?
It's really funny because I feel like I came to the realization through writing. Actually, I finished undergrad and I've been working for a couple of years and knew that I wanted to do some climate adjacent work, but I didn't know what I wanted to do. So I've been writing for a little while, and I actually interviewed a professor at Brooklyn College who does like wetlands research. And I was like, okay, we're done with the interview, but like I have questions about grad school. Like, what should I do? So talking to him actually helped a lot with kind of clarifying what I want to work on. I always enjoyed science, but science is big, it's fast. You can like everything, like I love biology, love physics. But the question is like, what do you want to do with that, right? So kind of getting some clarity on like what I wanted to do with that by like talking to people on the ground about how they were dealing with climate impacts kind of helped me figure out what I want to do. So that's kind of how I kind of came to this space. So like for me, like I'm really interested in like severe flood and like rainfall research is kind of where like my head is. So like that's like an interesting question in science, like in terms of science, but also like an interesting question in terms of impacts for people. So, but that was very much for me, just like kind of talking through and figuring out like what people are doing. So that's how I got here, to answer your question.
Boy, I love what you just described. Never let an opportunity go to waste. If you're in the field talking to scientists, you can learn a huge amount. Has anyone else had, by the way, Kara, had you had any, or actually any of you, when you were young, was there some interaction like that with a more seasoned researcher that propelled you toward your answer to that question? Did anything come right to mind? And Galen, I think were you about to say something?
Yeah, I mean, I guess I have answers on both of those points, but I'll just start with the first one. I mean, I think that, the question of what's the most important question and what should we be focusing our energy on really that's a political decision, right? As across, what the NSF is going to invest in, what the DOE is going to invest in, right? And so we are all scientists trying to do our best in that context, but also trying to make the case that more investment in science is clearly needed, and across all things, like in terms of higher energy physics. Yes, there's a lot that maybe is rather esoteric, but there's also things like the big experiment that happened on the NIP where we're getting closer to fusion. That's not going to solve climate change in the near future, but that is an important direction. And there's a lot of side benefits to doing that work as well. I just think in general, the choices we make as a country determine the problems that we're working on. And this distribution between doing science, thinking about the future, dealing with aid for people today, doing adaptation. There's a lot of decisions that we collectively have to make. And our goal as scientists, I think, is to try to provide information that helps support that decision making. But it is an all hands on deck kind of effort. And I think broadly, everybody in the society needs to be thinking about what we need to be focusing on. So yeah, that's my response on that point. Yeah.
And any other, and then on the point of inspiration or career advice, anything come to mind for you, or Kara or Ali?
I could go. I mean, I actually started out in quantum physics in graduate school, and I spent about 2 years working on a quantum computation experiment, which was extremely interesting. But I think at some point, similar to what Chad talked about, I just had a feeling like I wanted to, move towards working on something, like using these skills that I had developed to work on something that I felt like was, kind of the problem of my generation, like thinking about the atmosphere and the climate. So I think for research can be challenging, and then like having that answer to why, like having that answer to like, why am I doing this every day? And having it be like something that's so important on a global scale, like to understand the climate, to understand how the atmosphere works, like to have this knowledge be something that we can pass on to future generations. Like that has been like, kind of like the reason that has really motivated my like interest in this field.
I think that's a common thread here. It sounds like certainly Galen expressed that too. And you're making me think about Adam Sobel, who's a climate scientist at Columbia, who a couple of years ago wrote a commentary on what he calls usable science. He was kind of focused on basic climate science related to hurricanes and climate change, really important, but he really shifted his own priorities toward adaptation, resilience, the application of that knowledge. And I don't think it's a hashtag yet, usable science, but it probably could be and should be. It's one way to sort of focus your, to keep one focus. I try to, as a journalist, I went through this transition. I realized through a lot of reporting on behavioral and social science that just doing more of this basic storytelling, it wasn't very useful anymore in the context of what needs to happen around climate change. Because the typical story is too neat and clean. You can't capture all these dimensions, just like with the work you're doing at LEAP and Allen Institute. So I try to foster conversations. It's really part of my journalism, as much as writing. Being useful at a time of great consequence is certainly something I would hope some more basic physics wizards would think the same way. But everyone has a role in a different orientation. We're getting toward the end here. There was one last question that I wanted to throw at you. That's probably too rude to put before you. Let's see. Yeah, here, Maynard Clark. How can all this integrate with or be integrated with population health and public health interests? I think public health is certainly a straightforward part of adaptation. What's the next round? In other words, through this year, I'll be doing more of these webcasts. So if you each, thinking about what we've been speaking about today, could add, like, who else should be in the conversation to make that bridge more real, not just for health, but for the other disciplines. What would that look like? So how can all this integrate with or be integrated with population health, public health interests? Anyone want to jump on it? Okay, Pierre.
Yeah, I think actually we have some insights as to how that could work. In fact, there was the work from Jeff Shaman here and Mark Kane that was really revolutionary at the time when they started integrating some climate indices such as El Nino as a way to predict malaria. So there's a very clear link, right, between diseases, especially, for instance, mosquito-driven, and climate change. Even for COVID, right, we know that there's a very strong seasonal effect as well, right? So I think there's a lot that can be integrated. One of the bottlenecks here, I would say, once again, is the fact that climate data can be difficult to get access to, right? It's very difficult to grab the data. The format is a bit complicated. It's a huge amount of data, and providing a platform that can be easily accessible. And that's one thing we are trying to do in the center, is providing a cloud-ready platform so people can really basically ingest and use these data at scale. And public health is a great application of that.
And then it's a fairly straightforward process to get that, to make sure people are aware of that in those relevant fields. But that's a great, the idea of openness to the data and the model processes seems really important. which wasn't always the case. Looking back at the history of climate models, there were proprietary aspects, and data haven't always been open. So that certainly feels key. Galen or anybody else have a thought about this integration, convergence? It's like the opposite of convergence. You converge to push the science forward, but then what's the other word? It's not out. The expanding the awareness, I guess. That knowledge transfer is one clunky phrase for that. But
I mean, I think I think we all need to learn how to do things like this podcast and try to communicate what we're doing to the greater community. We need to talk to the public, to younger people, to policymakers in DC, right? So I think we all need to be out there trying to communicate and engaging in the conversation. And really not just saying, oh, here's the information, throwing it over the wall, as Pierre's saying, trying to build tools that actually make it useful to people and understand what the real needs are and to do that work. And again, it is a good thing about the SDC that they actually support that effort. Most research grants wouldn't support it at the level that we have the ability to do in the LEAP project. So we're very excited about doing that.
That's great. Well, Maynard Clark also mentioned specifically Climate Echo at University of New Mexico is an integration of public health concerns and climate-related information. So that would be I could probably help to build some bridges there to see, get in touch with them about what might be interrelatable here. I'm just going to show I've got the website here. So that's at the University of New Mexico. It's a project integrating public health and climate information. Well, this has been a rich and rewarding initial conversation about LEAP, which is an effort to leap forward in using AI to improve the applicability of climate models output to real-world problems on real-world timescales. It's a fantastic enterprise. I'm really glad I'm part of it. Thanks today to Pierre, Galen, and Kara for being part of this from the Columbia end, and to Ollie Wattmeyer from the Allen Institute Artificial Intelligence Group, the climate side, and especially to Chad Small as you get going, both on the journalism and on your scientific inquiry. I'd love to stay in touch, and we can talk further about frontiers for journalism related to this too. One thing we've already talked about internally at LEAP is getting some journalists newsroom understanding of climate modeling, and like Jeff Shaman, actually, who Pierre mentioned, had worked with the New York Times on their pandemic models in the early days of the pandemic. So there was a newsroom science data collaboration. I'm sure there's possibilities there as well. Thanks to everyone again today. This is the Sustain What webcast in its third year, pretty much. In which we look at the intersection of complexity and consequence and try to drive forward conversations towards solutions. And the work that was discussed today certainly fits that bill. If you're watching now, the link you're watching on will be archived instantly when we're done. You can share it with others. You can get in touch with me about this or future episodes looking at that streaming distracting bar at the bottom. So just go back, click back, and get the information. And sign up for alerts through those links below. I hope everyone here has a successful and healthy end to your year, and lots to look forward in 2022 and 2023. Thanks again for being here. This is Andy Revkin, Columbia Climate School, from the rural Maine Bureau of the Columbia Climate School, signing off. Be well, everyone.